afternoon. On behalf of the Southampton Theory, Astrophysics and Gravity Research Center, or STAG for short, I'd like to welcome you to this year's public lecture. My name is Kostas Kenderis, and as a director of STAG, I will be your host this afternoon. So I'd like to start by saying a few things about the STAG Research Center. So the mission of the STAG Research Center is to foster and promote cutting-edge research that cuts across different fields. We do research from the very small to the very big, from the microscopic structure of atoms to the big large-scale structure of the universe. But another mission of STAG is to promote public awareness of fundamental science and to inspire the students of today, some of which are already here, to become the scientists of tomorrow. And as part of this mission, STAG organizes every year an interactive workshop aimed at secondary school and sixth form students, and one such workshop took place this morning. And in these workshops, we aim to explore and explain the mathematics and physics that underlies the research which is carried out by STAG. STAG also organizes an annual public lecture, which is given by a highly distinguished researcher that explores and explains the great achievements of fundamental science. And today we will hear from Professor Seiberg later this afternoon. But before we do this, we're going to have a little ceremony because of the STAG prizes. To celebrate the achievements of our PhD students, we award STAG prizes for best publication in the research areas of STAG and for public engagements. And I'm very delighted that the leadership of our two faculties, which support STAG, are here today. So we have the Dean of the Faculty of Social Sciences, Professor Jane Fockingham, and the Dean of the Faculty of Engineering and Physical Sciences, Professor Bashir Al-Hashimi, and they have agreed to present these prizes. So the prizes are books signed by our distinguished speaker, and they will be given to the students that awarded the prize this year. So I would like to first welcome Professor Fockingham to present the prizes for best publication in gravitational physics and the prize for public engagement.
Thank you. It's always a great honor to come to the STAG annual lecture and to celebrate our PhD students. Some of you might be a little bit surprised that the two faculties involved, one of which is social sciences. But actually, mathematical sciences are crucial for understanding all of the global challenges that we as a society are facing going into the future. So I'm absolutely thrilled that mathematical sciences and STAG is actually part of the Faculty of Social Sciences at the University of Southampton. And I'm also thrilled by our fantastic PhD students who are really doing amazing research and pushing the boundaries. So the first prize, I think, is for public engagement, and the nominated students are Joan Garcia Tormo and Lorenzo Zanisi. And the winner is Lorenzo Zanisi for participating and winning a silver award in STEM for Britain in the poster competition. His poster was selected from over 500 entrants, and it was presented in Parliament. He demonstrated that techniques used in astronomy may also be used in medical research. So really fascinating research. So congratulations. Second prize I have to give is the nomination for the best publication, and you can appreciate that with such fantastic PhD students, the competition was very tight this year, and the committee has decided to award one joint award in one category and runner-up awards in the other two. So for the best publication in gravitational physics, the nominated students are Ramon Sachs, apologies for the pronunciation if I get it wrong, Aaron Poole, Stanislav Smit, Marcella Ubingarden, and Alex Wright. And the winner is Aaron Paul for his work on gravitational radiation in space-times with cosmological constant. Aaron could not be present today, and his fellow PhD student Fabian Gittens will receive the award on his behalf. So, Fabian. Thank you. And the runners-up is Stanislav Smith for obtaining a new solution of supergravity theory. And again, unfortunately, Stanislav could not be present today. They're obviously really busy, these people that win prizes. And his prize will go to his supervisor, who will receive it on his behalf.
That's great. Okay, I'd like to thank Professor Falkenham and invite Professor Al-Hashimi to present the prizes for Best Publication in High Energy Physics and Best Publication in Astrophysics.
Ladies and gentlemen, good afternoon. It really does give me great pleasure to see STAG going from strength to strength. I remember the first time I was approached about supporting such activity, I wasn't too sure. Not because of the people involved, it is because I really did not know what it's supposed to be doing. But having looked at the quality of the research the PhD students undertake, over a number of years, I could only say that it really is of the highest quality. I'm an engineer, I'm not a physicist, but I could recognize some of the relevance the PhD students' research are doing and the impact it does. And gives me great pleasure also to see the interest in the annual public lecture, seeing so many people here, young and old, which is great. So I just want now to move on and introduce the prize for Best Publication in High Energy Physics. The nominated students are Jack Foster, George Constantinos, Ronnie Rogers, Sam Rowley, Alex Titterton. And the winner is Jack Foster for work on properties of scattering amplitudes. The runner-up is George Constantinos for finding a new supersymmetry anomaly. The selection committee also wished to make a special mention of Ronnie Rogers. The next prize is for Best Publication in Astrophysics. The selection committee decided to give a joint award to Marcia Wintergarden for work on the effects of nuclear burning in the envelope of neutron stars, and John Price for work on speedy time lags between X-ray and visible light emission in a growing black hole. John cannot be here today. His fellow PhD student Sam Manningham will receive the award on his behalf.
This is Marcella.
Thank you.
Okay, thank you. So it is my pleasure now to invite Professor Alex Neal, Vice President Education, to briefly open this STAG public lecture, and then I will introduce the speaker.
Good afternoon, everyone. I think probably almost everyone here knows that the mission of the STAG Research Centre is to foster and promote cutting-edge research in fundamental science, from the very small to the very big, from the fundamental microscopic building blocks of matter to galaxies and the universe as a whole. And for a university like ours to have a diverse portfolio in science, ranging from this sort of absolutely fundamental science through to very applied science, and diverse too across a whole range of subjects, is absolutely fundamental. It allows us to do the kind of research that we've heard about already this afternoon, and also to do research that has real impact. Impact, of course, comes in different shapes and sizes, and one of the missions of STAG is to promote public awareness of fundamental science, and crucially, to inspire the students of today to become the scientists of tomorrow. And as part of this mission, STAG organises interactive workshops aimed at secondary school and sixth form students. One such workshop took place this morning, I understand, and it's another one in a series, the aim of which is to explore and explain the mathematics and the physics that underlies the research carried out by STAG in a way that really inspires the next generation of scientists. That's impact. And there's another kind of impact represented by the annual public lecture that STAG organises, always given by a very highly distinguished researcher and dedicated to exploring and explaining truly great achievements in fundamental science. It's a delight to be here on behalf of the university to welcome Professor Seiberg, who's going to deliver this year's lecture. Thank you. Thank you.
Okay, it is time now to return to the main event of this afternoon. We are very delighted and honored to have Professor Nati Seiberg delivering this year's public lecture. Professor Seiberg obtained his PhD from the Weizmann Institute of Science in Israel. He's currently a professor at the Institute of Advanced Study in Princeton, and he previously held positions at the Weizmann Institute and at Rutgers University. I think it's fair to say that Professor Seiberg is one of the most creative and deep thinkers of his generation. He has worked on diverse topics, from string theory to quantum field theory to condensed matter theory and particle physics. And I think for the people that know his work, it's really very different than many other people. He has this uncanny ability to see hidden relations, so-called dualities, between seemingly different and unrelated theories. And this led him to find exact solutions of quantum systems, and this led itself into surprising applications to both physics and mathematics. And there are many breakthroughs which are attached to his name, including the Seiberg dualities and the Seiberg-Witten theory. He has received numerous honors and prestigious awards, including the MacArthur Foundation Fellowship, the Heinemann Prize, the Dirac Medal, the Breakthrough Prize in Fundamental Physics, and he's a fellow of the American Academy of Arts and Sciences and a member of the National Academy of Science. Today, he will tell us about the frontiers of fundamental physics.
Can you hear me? Is it on? So first, I want to be the first person to congratulate the young people. It's very encouraging to see all these brilliant people, and I wish all of you a spectacular career, either in science or wherever you want to go. I also want to thank the organizers of the event. It's a huge honor. When I was invited, I was kind of skeptical whether to accept or not, and my wife was clearly against me accepting it. But then I saw the list of previous speakers, and that decided it for me. The other thing is that I arrived, this is my first time in Southampton, so so far it has been quite interesting, and we've already had a number of excellent, very stimulating physics conversations, especially yesterday and this morning, and I'm looking forward to more interaction with the local leading physicists here. And you're very happy to have them on the faculty, and the students should benefit from them. Finally, I would like to thank all of you for coming, but especially the young people. I am really thrilled to see so many young faces, seeing young people interested in science, and I think it gives me hope, or convinces me further, that the future of science will be interesting, spectacular, surprising, and it will be in your hands. So what is physics? So what I give today is kind of a status report of where we are in physics. And in order to give a status report, we have to understand how we came to today, what happened in the past, and try to draw some lessons from the past about the future. So I'll go very far past. I'll start with the Babylonians, and I will go to very futuristic ideas. I will also span, so this will be physics or research over many years, but I will also span many orders of magnitude of scales. Some of them have already been alluded to by the people who introduced me early today. I'll talk about very, very short distances and very long distances. So in physics, we want to explain things at very, very different length scales. And whenever we talk about something, it's really important to completely understand what length scale we are talking about. And specifically, we'll talk about, in this talk, we'll focus on two extremes, the physics of very short distances. We'll talk about the structure of matter, going deeper and deeper into matter. We'll talk about molecules, atoms, elementary particles, and so on. And in the other part of the talk, we'll talk about increasingly large distances. We'll talk about the Earth, the solar system, galaxy, the whole universe, and so forth. Now, today, we are in a really unusual and almost unprecedented situation in physics. And it's very important to understand that. We have two standard models describing the two halves of what I said before, the physics of very short distances and the physics of very long distances. And these standard models work extremely well. Extremely well. And there isn't at the moment there's almost no contradiction between theory and experiment. In that sense, it's almost unprecedented in the history of science. There was only one similar case, and I'll mention it later, but in that sense, it's quite interesting and quite unusual. And this has led some people to say that maybe it's the end of science, or specifically the end of physics. Maybe there's nothing else to be discovered. And I'm quoting books that appear with the name, "There's a crisis of physics," "There's a crisis in physics," or "Physics is over, there's nothing new to be discovered." And some people even say that maybe physicists are just lost, completely lost it. If you take only one lesson from this talk, one takeaway lesson, is that this is completely, completely wrong. And what I'll do in the rest of the time here, is try to convince you that we are in a very unusual situation, but the future is guaranteed to be very exciting. And this is especially a lesson for the younger people in the audience. You can have a full career in science for the next 50 years or 100 years, and I guarantee you that physics will not be over in 50 years or 100, let alone today. And the reason for that is that, that's the but, the big but, that there are excellent arguments that there must be new physics. We have very sharp puzzles, interesting things we do not understand, and we have more experiments soon that will give us clues to how to proceed. So for these reasons, I'm quite excited about the future of physics. Now, here in the title of this slide, I said almost unprecedented. So why did I say almost? Because there was one situation in physics which was very similar to today. And I'm going to make an analogy between the situation then and today. And of course, history never repeats itself, but at least we can learn some lessons from it. And that was more than 100 years ago. And more than 100 years ago, in 1900, the British physicist Lord Kelvin gave a famous lecture. So first, let me say a few words about Kelvin. His original name was William Thomson, and he was one of the leading physicists of the time. He made fundamental contributions to electricity and thermodynamics. The Kelvin scale of temperature is named after him, and the Kelvin came because he was named in recognition of his achievement. He became the first Baron Kelvin. So he was a very distinguished physicist, one of the leaders of his time, and in 1900 he was asked to give a lecture summarizing the situation of physics at that time, summarizing where we are, how we got to where we are, and how he sees the future. And what I'll try to do today is imitate what Kelvin did more than 100 years ago. So the title of the talk was 19th Century Clouds over the Dynamical Theory of Heat and Light. So during the 19th century, physicists have done a lot of work, and they understood electricity. Maxwell's theory was already there. They understood thermodynamics. In fact, Kelvin was one of the people who contributed to that. And some people said then, well, maybe physics is all over because we understand everything so well. And Kelvin, in his talk, highlighted two clouds over 19th century physics. So the details are not important, but let me just mention the clouds. One cloud was the Michelson-Morley experiment. This is an experiment that eventually led to Einstein's theory of relativity. There was one little discrepancy, one little puzzle with the Michelson-Morley experiment. It did not quite fit with 19th century physics, and that was one of them. The second was a puzzle with something called black body radiation. Again, the details are not important, but this puzzle was one of the roots of quantum theory. So the revolutions of 20th century physics really stemmed from these two little puzzles. Everything worked very beautifully except these two details, and one might be tempted to say, oh, these are details, we don't care, or these details are too hard, we'll never understand them. In fact, this is 1900. The big revolutions more or less ended about 20 years later. So he was only 20 years before they were totally confused about these details. Now, some people interpreted Kelvin's, in fact, you can see it in print, some people interpret Kelvin's lecture as saying that physics is over. In fact, it's a fascinating lecture to read. I highly recommend that you look at it. And in his lecture, he completely understood the significance of the clouds. He understood that these clouds are the first sign of a big storm. In fact, two big storms. So these are clouds over the horizon. You might try to ignore them, but they tell you, watch out. Something very big is going to happen. And in fact, it did happen. So Kelvin realized the significance of these clouds, and what I'll do today is try to imitate Kelvin. I'll describe the successful theories we have, how we reach them, but I will also highlight the little details, these things that don't quite work, which tell us that there must be new physics that we do not yet understand, and we should focus on these details because we should view them as clues to the next step. In order to do that, I would like to put some flowchart of how research works, and this is especially for the people who don't participate in research. And of course, it will be a little bit oversimplistic. It will be only one slide, but it will be useful to keep this flowchart or this diagram in mind. So often research progresses in steps. The first thing is we collect data. We see some phenomenon, we start measuring. We measure whatever we can. We have lots and lots of numbers. A lot of numbers, and I'll give examples of this soon. The next step, somebody bright looks at the data and identifies a pattern. There's a simple formula, and now we no longer need all the tables of numbers because a lot of information can be captured by one simple formula. And that formula still has coefficients, some numbers there. We refer to them as parameters. So say we had 1 billion numbers that we measured, and now we have a formula, and the formula still has 3 numbers there, and these numbers need to be measured. But this is a huge advance, because instead of having the 1 billion numbers that we measured, we just have to measure 3 numbers and know the formula to reproduce everything else. But we still don't know why the pattern is there. And if you think that this is kind of too abstract, I'll give a lot of examples in the rest of the talk. So then somebody else comes along, and he or she understands why the pattern is there. So we'll replace the pattern, which was discovered experimentally, by some new law of physics, a law of physics that underlies this pattern that was observed. And what remains to be understood are these remaining parameters, these extra numbers that appear in the formula. They are still not understood. These are the kind of input to the theory. So we explore these extra parameters, and then we find a few more of them, and we collect more data, and then we go back to the beginning. So a lot of examples of research in science progresses through this pattern. It's not always phrased in this language, but it's easy to see that this is kind of a general framework of how science progresses. And now I'm going to give two examples that I will use both the examples themselves, but I will also present them using this pattern of how research, or this sequence of phenomena. So I'm going to start with the motion of the planets. So step one, remember, was collecting data. So from ancient time, people looked at the sky, they were fascinated by the stars, and they saw that the stars move around in a very complicated way. So this is from the ancient Babylonians. This is an Assyrian star map from Nineveh. And these are the ancient Greek. So they were all very interested in motion of planets, and they collected a lot of information, and they tried to organize the information in a coherent fashion. They tried to find this pattern. And what they talked about is epicycles. They had the idea that the universe is made of circles moving within circles, kind of very complicated structure of circles within circle. They did succeed to describe the data using this pattern, but that clearly was not the most efficient way to do that. The more efficient way to do that, and the conceptually better way to do that, came centuries later. This is around the 17th century. The pattern was understood. And the main idea was the heliocentric model. The sun is in the middle, and the planets circle around it. And that was understood first by Copernicus, and then Galileo and Kepler really identified the pattern completely. So the sun is in the middle, and the planets move in ellipses around the sun, but there are still some numbers that are not explained by the theory, and these are the sizes of the orbits of the planets. So we still have 5 planets were known at the time. So each ellipse has 2 radii. So these are 10 numbers that have to be fed into the picture of the motion of the planets. And using that, and the fact that these are ellipses, Kepler, and earlier the others, could really predict a lot of information about how all these planets move and all the complicated trajectories. So the epicycles are gone. We have a much simpler model. This is the pattern. Then there are 2 things to do. Recall my flowchart. One is to understand where the parameters come from. Where did these numbers, the radii, come from? And the second, why do planets move on ellipses? Well, for that, let's first discuss the first one. What is the origin of the parameters? So Kepler had a beautiful idea. Of all his ideas, this is the one he was most proud of. So he has his famous 3 laws. This is usually not mentioned in the textbooks, because as you will see soon, it's completely wrong. But there are many lessons to be learned. There are always many lessons to be learned, even from wrong ideas. Great physicists and great people in general, even their wrong ideas, are interesting and worth paying attention to. So Kepler said, we know of 6 planets, and there are 5 Platonic solids. The Platonic solids are these nice shapes that the Greek knew about. These are shapes that all the sides are the same, all the edges are the same, and all the faces are the same. And there are 5 and only 5, the tetrahedron, the cube, icosahedron, octahedron, and dodecahedron. And it's a very deep result known to the ancient Greek that there are 5 and only 5 Platonic solids. So Kepler said, let's take the Platonic solids and inscribe them inside the sphere, and then inscribe another sphere inside it, and then put another Platonic solid inside, and then inscribe them another sphere inside. So altogether, we are going to get 6 spheres, kind of 6 concentric spheres, with these Platonic solids there. And the radii of the motion of the planets will be the sizes of the spheres. What can be nicer than that? Very deep mathematics, that there are 5 and only 5 Platonic solids, connects with the fact that there are 6 planets. And what could be nicer than brilliant, deep mathematics explaining heavenly objects? Well, it's completely wrong. It's completely wrong. First, as Kepler himself knew, the planets move on ellipses and not on circles. So that's kind of dead on arrival. Second, the numbers didn't quite fit. So he calculated what the orbit should be based on that, and it's completely off. But the real killer was the fact that we have more than 6 planets, and there are 5 and only 5 Platonic solids. So today we understand that the question is the wrong question to ask. This is an interesting lesson here. The the solar system has these parameters, these sizes of the orbits of the planets. These parameters are not fundamental. The fact that the planets move on ellipses, this is fundamental and deep. But the size of the orbit is not fundamental, it's not deep. It's just an accident of this particular solar system. There are other solar systems out there in the universe which have their own sun and their own planets circling around them, and the radii there are different, and there are lots of them. So there are different numbers, and that's our solar system was created with these numbers, and one should not look for any deep meaning for these parameters. So this is one of the lessons, that maybe some of these parameters, these numbers that are input to the theory, we should not look for a deeper explanation of them. They are what they are because that's they are. The second direction to go in research, I said that after we have the pattern, is to understand the underlying law. What underlies this motion of ellipses? That was again done here in Britain. The main person is Newton, and Newton invented classical mechanics. At the time, it was called celestial mechanics. It was called celestial mechanics because it was invented primarily to explain the motion of objects in the sky. And Newton explained the pattern. This is beautiful because Newton understood the laws of motion of bodies. He also understood the gravitational force, the attraction between planets, the planets and the sun, and he wrote formulas from these. And out of these, he could derive the ellipses along which the planets move. So now we don't need to postulate that the planets move on ellipses. We just need to postulate Newton's laws, and everything follows from that. Now, Newton was not satisfied with that. He was very concerned still about these parameters. Why do the radii have the size they have? So, in particular, he asked himself, are the parameters stable? So he derived that the planets move in ellipses by taking into account the force between the sun and, say, the Earth, or between the sun and, say, Venus. So taking the force between these forces, you can derive that the planets move on ellipses. But Newton, being brilliant, he asked himself, what about the force between the sun, between the Earth, say, and Venus? What about the forces between different planets? And these forces, Newton realized, will destroy the solar system. The solar system is unstable. These forces can knock any one of the planets off its trajectory, either send it into the sun and it would burn, or will kick it out of the solar system, and then all of us will die. So Newton was very concerned about this question, and being a religious person, he offered a solution. And this is really one of the most amazing things, I think, in the history of, at least in Newton's life. He was absolutely brilliant. He understood the laws of, these great laws of physics. He understood the gravitational force. He understood how bodies move, Newton's laws. And then he did not trust his own theory. So what Newton said, what happens if the trajectory slightly deviate? Eventually, the solar system will fall apart. So being a very religious person, Newton thought that every once in a while, God comes in and adjusts the trajectories of the planets. So God lets the planets run their course, but every once in a while he comes, or she comes, and realizes, well, Venus is not quite where it should be. Let's move it to where it should be. And the historian Michael Hoskin had a nice way of describing it. He said that God demonstrated his continuing concern for his clockwork universe by entering into what might be described as a permanent servicing contract for the solar system. So today we know that Newton's concern was completely right, showing again that what a great physicist he was, that even when he was wrong, it was still very interesting. And the solar system is indeed unstable. It's unstable for precisely the reason that Newton was concerned about. However, the time scale for the instability of the system is much, much longer than the age of the solar system, and therefore we shouldn't worry, at least until tomorrow. I think we're safe. So this is my first example of how the pattern works. We're starting with collecting data, finding a pattern with parameters, understanding the underlying reason for the pattern, and then we still have the remaining questions of the parameters, which we discussed a little bit. The second example I'm going to give is chemistry. And we'll follow the same sequence of events. So over the years, people collected a lot of data, knew about a lot of materials, and they measured their properties, how they behave under stress, how they behave as you heat them, as you stretch them, and so forth. What happens when you mix them together. A lot of information, including a lot of work that was done by the alchemists. Again, the work of the alchemists was misguided. They wanted to create gold, but even though it was misguided, they've collected a lot of information. And a lot of information that was understood at the time was created by these alchemists, which again showing that misguided work can still lead to useful things, sometimes not in the context where it is invented. So then came the pattern. The pattern came about 150 years ago, in fact, exactly 118 years ago. It was in 1869 by Mendeleev. This is Mendeleev. And Mendeleev understood that all the materials in nature should be divided into compounds and elements. So we should really focus only on the elements because the richness of materials that we see around us come from different compounds by putting the same elements in different ways. And the deeper structure is underneath with the elements. And he found a pattern, and this is the periodic table. It appears on many t-shirts. It's a very popular thing. And he arranged the elements that were known at the time in such a table. In fact, some of them were not known, so he had to leave gaps. And as we move to the right in the table, the elements become heavier and heavier in such a way that in the same column, the elements have the same property, like they're all metals, or they have similar chemical properties. So this is a huge advance. Instead of thinking about literally billions of different materials, there are less than 100 elements, and these elements are arranged in such a beautiful pattern. But Mendeleev did not know the origin of the pattern. Why are the elements arranged in this form? So there's a pattern. The pattern needs to be understood. This was a huge advance. The pattern was a huge advance. We still call it Mendeleev's periodic table. But there's a clear question that needs to be answered. Why do we have the pattern? Here it took 50 years. It's really a long time from the pattern till it was understood. And the pattern was understood in quantum mechanics. They understood the structure of the atoms, and the atom was understood to have a nucleus. This is not written to scale. The nucleus was made out of protons and neutrons, and around the tiny nucleus, there are electrons circling around, and the difference between the different elements is how many protons and how many electrons they have. And then, using the rules of quantum mechanics, Mendeleev's table can be derived. This was a huge advance. And you can ask, when did this happen? Well, I think we can put the first timestamp to be the first Solvay conference in 1911. This was one of perhaps the first, or at least one of the first, scientific conferences. The idea of scientific conferences was invented only about 100 years ago, even though people have been doing science for millennia. And Ernest Solvay was the benefactor. He gave the money to organize the conference. He was very interested in science, and he could not attend this famous photo. He couldn't be there for the, so this is him. This is Mr. Solvay. So he couldn't attend the meeting, so they left the seat open and took the photo, and then he took his photo later, and they put it together. This was arguably one of the first few Photoshop jobs that happened. And all the leading physicists at the time, including Marie Curie, Poincaré, Planck, who will figure later in the talk, Rutherford and Einstein, who will also figure later in the talk, came there. And it's, again, a fascinating reading, especially for people who know quantum mechanics. What's fascinating about it is how confused they were in 1911. They were absolutely confused. They talked about radioactivity, and they didn't understand what was going on. They asked the wrong questions. They were not even sure about the structure of the atom. It was a complete mess. In 1927, there was another Solvay conference. By this point in time, almost every one of these questions was completely understood. This was stunning development, and it's quite amazing how they achieved so much over so few years. As you can see, the conference is bigger, there are more people, and if you can recognize some of the faces, they aged a little bit. And among the participants, Schrödinger, Dirac, Bohr, Planck, Curie, Lorentz, and again Einstein, except that at this point in time, he's sitting here in the front row, being a world celebrity at that point. So this is quantum mechanics, but there are still parameters to understand that are not understood. These are input into the story. For example, the mass of the electron, or the mass of the proton. So quantum mechanics doesn't explain that. So we understood the pattern that Mendeleev found, where we had all sorts of parameters like the masses of the atoms and so forth. We replaced that by a deeper theory, and we still have these parameters that need to be understood, like the mass of the electrons, the masses of the nuclei. So by now you have seen going through this sequence of collecting data, finding a pattern, finding the underlying reason for the pattern, and there are some parameters that need to be understood. We've seen two examples of that. And now let me go to, for the rest of the talk, I will describe the situation today, keeping in mind these examples. So we'll discuss two standard models that were developed during the past few decades. One of them describes physics at very short distances, in fact, much smaller than the size of the atom. And we really have a very detailed understanding up to very short distances, going down to very short distances, up to about 10 to the minus 19th of a meter. It's about 1 billionth the size of an atom. And this is quite amazing that we can go to short distances. And I'll review what we know about it soon. The second standard model we have today is in cosmology, describing the universe as a whole, describing the very long distances. And here again we have a nearly perfect model that works at huge distances, up to 10 to the 26 meters. Notice this huge span of orders of magnitude that we understand, and that's what leads people to say, wow, this is really amazing, and it is. But that's not the end of it, because we would like to understand what happens at shorter distances than this, and what happens at longer distances than this. And I'll say a few words about that. So let me describe the two standard models. So I'll start with particle physics. This is a very long and beautiful story, and I will spend only a few slides discussing it. It explains phenomena. It describes the elementary particles and the forces that act between them. And at least in principles, since we understand what happens at short distances, we can just repeat that for more and more complicated systems. So at least in principle, most of science can be derived from it. If we understand the particles, we can put them together and understand atoms and chemistry, and maybe even biology, and so forth. I underline here, and I said at least in principle, because we understand the fundamental equations. We have no doubt that the fundamental equations we know are correct. The equations are correct for reasons I will soon elaborate on. But the equations are so complicated that in most cases we can't solve them. So knowing the equation, the fact that we know the equations is very nice and gives us comfort, but it doesn't help us using them and explain everyday phenomena. So that's why, this is another reason why physics is still interesting. But this is a huge achievement. So where did the data come from? Well, we need, in order to understand physics at short distances, we need a microscope or a magnifying glass that will allow us to have very good resolution at very short distances. And to do that, we use accelerators. And the accelerators collide protons or electrons. They collide, bring two of them together, and we observe the debris. Then we do it again and again. So they collide again, and we look at the debris. We look what particles come out, at what energy they come out, how often this happens. Every time, it's a little bit different. And we look at all this information, and this information tells us something about the forces that act on these particles, and their mass, and so forth. Now, in reality, this is not what the collider looks like. This is what it looks like. This is the largest experiment we have today. This is the LHC, it's the acronym for Large Hadron Collider. It's in the laboratory called CERN. It's acronym, again, in French, of European Center for Nuclear Research near Geneva, Switzerland. And in fact, I'm a little bit imprecise when I say that this is what it looks like, because this circle here is not visible. So it's 100 meters underground, and this was added to this aerial photo here. So this is the accelerator. It's 100 meters underground. The circumference is 27 kilometers. It's really huge. And just to give you a scale of how big it is, this is the runway of the Geneva International Airport. And you see that it's a lot smaller than the accelerator. So this is the experiment. This is where the data comes from. And taking all the data, we have this standard model. And the standard model is based on principles. The principles are quantum mechanics and special relativity. Recall these principles of the standard model, quantum mechanics and special relativity, are the outcome of the two clouds that Kelvin had. So there were these two clouds, two things that didn't quite work. They led to quantum mechanics and special relativity, and these are now the principles of the standard model of particle physics. And we have matter particles, electrons, quarks. Electrons move around in the atom around the nucleus, and quarks are inside the proton and the neutron, and there are others. I'll soon elaborate on that. And there are forces. The electromagnetic force was understood already in the 19th century. And the strong and the weak nuclear force were understood in the 20th century. And they are all merged together in this beautiful, coherent story of the standard model. And again, we have these parameters, these numbers that the standard model does not predict and we need to understand, but we feed them in, like the masses of the particle and the strength of the force. Let me say a few words about the matter particles. These are the matter particles of the universe. There's no question that this is the correct story. There's huge amount of evidence for it. So this is the electron. That was known early on. Quarks were understood in the second half of the 20th century, and they come in different names: up, chum, top, down, strange, bottom. And the electron has friends called muon and tau. And there are also three peculiar particles called neutrinos. The details here are not important for our purposes, but the important thing is that these are the elementary particles of our universe. Everything is made out of these particles. And the particles can be arranged in a table. As we move to the right, the particles are heavier and heavier. And all the particles in each row have the same properties. They have the same electric charge, for instance. So we can call that the periodic table of matter particles. Notice how similar it is to the situation in the case of Mendeleev. There is a clear pattern, but we don't understand why the pattern is there. We don't understand why we have this periodic table. This is a big open question that I'll talk about it soon. Sorry. The last particle in the standard that was discovered in the standard model is the Higgs boson. This was the combination of a lot of work, both theoretical and experimental. We can think of the Higgs boson as being the keystone of the standard model. A keystone is the central stone at the summit of an arch that appears at the top. It gives the whole structure to hold it together. It's locking the whole structure. And similarly, the Higgs boson is essential in the standard model. It was the last particle to be discovered. It was discovered in 2012. So it was discovered in 2012 at the LHC. And this was a big celebration because after that particle was discovered, all the elements of the standard model have already been discovered. And this is a photo from the press conference where the Higgs discovery was announced. And that appeared all over the world. This was front page in the New York Times when it appeared. And Francois Englert and Peter Higgs, he's British. So these two people are the theorists who predicted that. It took about 50 years from the prediction of the Higgs boson till it was discovered experimentally. So we should be ready for long time spans from prediction and experiment. And they received the Nobel Prize in Physics in 2013. Notice that Englert and our host, Costas, have the same tie. In fact, I also have the same tie. So we discovered it this morning. It was not planned. It was designed, this tie was designed by Gerhard Hooft. He's one of the greatest living physicists. I think this is correct. He's one of the greatest living physicists. He's one of the founders of the standard model that I've just described. And among his awards, he received the 1999 Nobel Prize in Physics, and he gave the 2014 STAG lecture. I think these are his two main awards. And these ties that he designed, it depicts the particles of the Standard Model, were given as gifts to the guests in his 60th birthday, and that both Costas and I attended. I guess there were other people in the event who didn't get it, and they were discriminated against. I am told that they still have a few of them, so you should write to them and ask them for the tie. It's actually quite nice. So going back to more serious business, we have a small number of parameters, like the mass particles of the masses, and we explain tons and tons of experimental results, literally trillions of experiments. Every time you use any electronic device, you check the Standard Model. You use your cell phone, you use your computer, you check the Standard Model. If you trust your laptop, you trust the Standard Model. So this is quite interesting, and it is an unprecedented success. I said before that most quantities cannot be computed because the equations are too complicated, but there are a few quantities that can be measured and can be calculated to extreme accuracy of 10 significant digits, and the 10 significant digits agree. There is no other branch of science with such accuracy. There's nothing even close to that. So it's 2.3574, whatever, 10 significant digits. Every one of them tests something, and the fact that the whole thing works shows that we really know what we're doing. It's not a coincidence. This is really unbelievable, and this is a fantastic achievement of mankind. But we shouldn't rest on our laurels, because we have open problems. In the language of Kelvin, these are the clouds on over the model. So these are issues that are not yet understood, and they need to be understood. So first of all, we've already mentioned that there is a pattern. There is a pattern for all these elementary particles, quarks, electrons, and others. We don't understand why the pattern is there. Last time we faced a situation like that was the time of Mendeleev, and explaining the pattern was a huge thing. That was quantum mechanics. It was also one of the clouds in the time of Kelvin. So that was quantum mechanics, and we can hope that understanding this pattern will be equally exciting, will be equally important. So this is something, it's a kind of a clue, and in more detail we have to understand why we have these particles, why do we have the pattern, why do we have these three forces that I mentioned, the electromagnetic, the strong, and the weak force? Why not 5 forces? What predicts, what determines the strength of the force? And so forth. There are also some more technical reasons to believe that the Standard Model is incomplete. This is slightly more technical. First of all, the Higgs boson mass is unstable. This is a little bit reminiscent of Newton's concern about the stability of the Standard Model, which is, again, something that's very deep. This is a question that we still need to address. In the Standard Model, neutrinos don't have a mass. They have 0 mass. Experimentally, neutrinos do have non-zero mass. So the mass of the neutrino is already in contradiction with the Standard Model. So we know that the Standard Model is not complete, and it does not incorporate gravity, and I'll say more about that soon. And very soon, we'll have more information. So the LHC will have a slightly higher energy. There will be more data. More data will give us more resolution. We hope that something exciting will come out. We can never be sure. And there's discussion of major upgrades to the accelerator, and even some discussion about building new, bigger accelerators at higher energies that will probe nature at much shorter distances. If they discover something exciting beyond the Standard Model, this will give us clues how to proceed. So this was a lightning review of the Standard Model of particle physics. Let me switch now to the second Standard Model, the Standard Model of cosmology. And again, this is a beautiful story, and I will review it only very briefly. I will not do justice to it. And the model describes the universe as a whole. If before we talked about what happens at shorter distances, now we go to ask what happens at very long distances. We discussed the Big Bang, how the universe started. If you wish, this is the question of creation of the universe, how the universe behaves at very, very short times, maybe with the creation itself. And we also address the question of how it evolves, how galaxies were formed, how stars were formed, even how the various elements that we see around us were formed. We have an understanding of what happened from the early on when the universe was only a fraction of a second old. This is, again, quite remarkable. We discussed it at lunch with some of you. About a decade or two ago, this was a complete mess. Nothing worked. Now we have a very coherent picture. People discuss whether the second or third digit has one value or another, but these are details compared with the confusion of only a few decades ago. This is to show you that this thing is still evolving very rapidly, and I expect it to continue to evolve in an exciting way. And we expand also the origin of the matter in the universe, how galaxies are formed, and stars. So where the information come from, as I discussed in particle physics, it comes from accelerators, which are kind of a microscope or a magnifying glass. Here, we need telescopes that look very far, and there are roughly two sources of information. The two kinds of telescopes, quote-unquote telescopes. So we all know that if we put a filter in front of us, only one color is transmitted through the filter, and other colors are blocked. Similarly, we can look at the sky with different filters, quote-unquote filters, and look at different wavelengths. This is the analog of different colors. And the most interesting one, or one of the most interesting one, is looking at the universe and see cosmic radiation. This is microwave radiation, the same kind of radiation that exists in your microwave oven at home, but we are kind of in a bath of such radiation coming to us from all directions. This was discovered about 50 years ago, maybe 60 years ago, for the first time. And when people looked at it through the sky in different directions, it looks almost uniform. So if it came from a star, it would not be uniform because it would be a lot stronger where the star is, but this is almost uniform. And only recently did the fact that it's not exactly uniform, was this fact discovered, that the radiation is not exactly uniform. The change in the radiation, in the intensity of the radiation from one direction to another is about 1 part in 100,000. These are tiny changes. So first, it's surprising and amazing how uniform it is across the sky. And then it's surprising and very interesting that it's not exactly the same. So the fact that the radiation is not exactly the same was discovered by satellites. You need a more detailed analysis that cannot be done from Earth. The first measurement was done, forget the year, but it was done by a satellite, acronym COBE, Cosmic Background Explorer. And for that, there was a Nobel Prize in Physics in 2006, awarded to John Mather and George Smoot. The latest, the state-of-the-art experiment is shown, the results are shown here. The different colors represent roughly different intensity. And these measurements come from a European collaboration. And the satellite of the European Space Agency, it's called Planck satellite, named after Max Planck, who appeared earlier in the talk, and he will also appear later in the talk. And by looking at these small variations of the microwave radiation, we get a detailed picture of the early universe and how it evolved and what the universe is made of. So we'll soon come back to this. This is one source of data when we look at the sky in microwave. The second source of data is looking at survey of supernovae. And I put here 3 people, Adam Rees, Saul Perlmutter, and Brian Schmidt. And for their discovery that I will soon describe, they received the 2011 Nobel Prize in Physics. In fact, Brian Schmidt gave the 2015 STAG lecture. So what is a supernova? Supernovae is the plural of supernova. These are exploding stars, and the explosion is so strong and so violent that it can outshine the galaxy in which it happened. And since it's so strong, the light can arrive here at Earth and can be detected. And what these people did was to look at these faraway galaxies, and they could do that using the explosions that happen in them, and they measured how far the galaxies recede away from us. And by doing that, they learned that not only does the universe expand, as we had known earlier, but the expansion of the universe accelerates. This was a big shock at the time. It's still a big shock that the universe accelerates, and we don't fully understand why it is so. There are various ideas. People call it the cosmological constant, but this was a major discovery. So these are roughly two sources of information. And putting these together, we have the standard model of cosmology. And again, we have principles, some other elements, and some parameters. So the principles are general relativity, and the fact that there was a Big Bang. These are roughly the principles. And we get a composition of the universe. This is the composition of the universe. The matter that we are made of, the matter that the standard model of particle physics describes, is about 5% of the total budget. Only 5% of the total energy in the universe is in these particles. And again, we said that earlier, how we first thought that the Earth was in the center, and the other stars move around us. Then we became a little bit less significant because the sun is more important and we just move around the sun. And then there were galaxies, and we're just at a random point in our galaxy, and there are many galaxies. We're totally insignificant. Now we see that this whole thing that we have been talking about is about 5% of the total. We are really made out of insignificant stuff, and we are in an insignificant place. Then we also have roughly 27% dark matter. This is more matter, just like our ordinary matter. We don't fully understand what it is. In fact, we have no idea what it is. This is more matter out there, and it's dark because we can't see it. Light, it doesn't emit light, but we have no doubt that it's there. We know where it is. We know how much of it is there, but we have no idea what it is. So these are puzzles that we'll need to understand. And then about 70%, 68.3%, is this dark energy, this mysterious force that makes the universe accelerate. So altogether, we have a beautiful and coherent picture of the universe, works extremely well, but there are open problems. And again, connecting to Kelvin, these are the clouds over this model. So we need to understand what is this dark matter. I said earlier that in particle physics, we know some particles and we know how they interact. We know the forces between them. We discover them at the LHC and so forth. The fact that there's dark matter tells us that there should be more stuff out there, more stuff that we have no idea what it is. What is this dark energy? Why do we have this force that pushes galaxies to expand faster? And we have a pattern, and we have these numbers. Why do we have these numbers? Why our stuff, our matter, is 5% of the total and ours is 7%? This is something to be understood, and I think it's fair to say, there are people in the audience who know more than I, but I think it's still fair to say that we have no idea. Then there are deeper questions about what happened even earlier, deeper questions about the origin of the universe. So one leading idea is the question of cosmic inflation, that very early on, when the universe was a tiny fraction of a second old, there was a rapid expansion, much more rapid than today. And by doing that, some of the pattern that I described earlier can be explained. So it's a beautiful idea. It has some experimental confirmation. However, there are still many puzzles that are not understood. So these are kind of the clouds or the open questions. And very soon we'll have more data that will guide us how to proceed. So it's the same thing. Collected data, we understood something. It works very well. There are a few things that don't work. And we need more data in order to understand a better theory, a deeper one. So one frontier is the following. I said before that we can look at the sky by putting a filter in front of the telescope that will transmit only one color, or only one wavelength, or only one frequency. Instead of that, we can put a Polaroid glass in front of the telescope. A Polaroid glass that will transmit light only with one polarization. And you know from Polaroid glass, you rotate it and things look a little bit different. You can look at the same microwave radiation that I described earlier, and try and put a Polaroid glass in front of that. Well, it has to be a little bit more sophisticated than the Polaroid glasses that you get in your local store. In fact, it looks like this. This has all the Polaroid glasses that you need. This is a telescope in the South Pole that looks for this polarization in the microwave radiation. And using that, so they keep collecting data, and hopefully they will tell us something interesting in the near future. The second source of data is the LIGO detector. So far we talked about observing the sky with light or electromagnetic radiation, different kinds, microwave, visible light, etc. These people measure gravitational radiation that comes from the sky. And the three founders of this detector, it's called LIGO, is Laser Interferometer Gravitational Wave Observatory. The three founders were Rainer Weiss, Barry Barish, and Kip Thorne, and they received the 2017 Nobel Prize in Physics. And Rainer Weiss also gave last year's STAG's lecture. So I'm stepping here, hard shoes to fit. So this is the standard model of particle physics, but I've not yet mentioned the biggest conceptual question. So we discussed particle physics and the challenges there and the open questions, and we talked about cosmology, the universe as a whole, and the questions that it poses, both the successes and the questions that it poses. But the biggest conceptual question is the following. We discussed two standard models. One of them uses quantum mechanics and operates at very short distances. The other uses general relativity or gravity and operates at very long distances. We shouldn't have two standard models. We should have only one standard model. We need to put these two models together, and we need to understand how to combine the ideas of quantum mechanics and Einstein's theory of relativity. These are two principles of nature that we know are right. Everything around us depends on them, and we still do not know how to combine them together in a coherent way. So where will we look for, where will this be important? So quantum gravity is relevant at very, very short distances, or at very short times, about 10 to the minus 35 meters, or times of 10 to the minus 43 seconds. This was understood more than 100 years ago by Planck, the same Planck we discussed earlier twice. He was in the Solvay conferences, and he was the satellite, the European satellite is named in his honor. And he calculated early on in the early days of quantum mechanics, the Planck, what is known as the Planck scale, telling us that once we understand physics at 10 to the minus 35 meters, this will amount to understanding how to combine quantum mechanics and gravity. Equivalently, when the universe was 10 to the minus 43 seconds old, the ideas of quantum gravity should be important. So the ideas of quantum gravity, this is the holy grail. This is really the creation of the universe. Understanding the creation of the universe is understanding physics at these short times. And the best candidate we have to address this question is a theory called string theory. This is a huge topic, so I'll be extremely brief. This is a topic for a separate talk, maybe several talks. And over the last several decades, we've seen enormous progress with amazing insights that give us reasons to think that we are on the right track. This is a good theory of quantum gravity, and very important work in this direction is being done here at Southampton. So it's deep physics, and here I would like to emphasize that it has already had huge impact on other branches of physics and on mathematics. And this is one of the hallmarks of a deep idea. A deep idea in science, and there are many examples over the years, people try to solve a problem, and they did something, and they either succeeded or they didn't. In most cases, they succeeded. But then the solution turned out to be very deep and have implications in other branches of physics they didn't even know about at the time or did not attempt to solve. Newton's calculus is one example. Calculus is very deep, and the reason we say that calculus is very deep is it appears everywhere. It appears in branches of knowledge that Newton didn't even invent at the time. It explains motion of bodies. It explains, it's useful in quantum mechanics. Even in the social sciences, people use calculus. So this is an example of a deep idea. Similarly, string theory, not only does it give us quantum gravity, it also has already had a lot of impact in other branches of physics, in condensed matter physics, even in astrophysics, but primarily in mathematics. The mathematics that string theory produced turned out to be extremely deep. For me, this is one of the signs that we are on the right track. It's hard to imagine that something so deep, producing so many good ideas, surprising ideas, unexpected, unintended ideas, is misguided. But with all the success, there are still some challenges. We do not understand the principles of the theory. And since this is physics, we need to have experimental confirmation. We don't yet have experimental confirmation. And we have to be ready that this will take a long time. Such deep questions take a long time. This is not a reason not to think about them, but we should not expect, like in industry, you're judged by the last quarter. Don't expect this problem to be solved in the next quarter. This will keep physicists busy for at least a century or two. This is my prediction. I'll be shocked if it's less than that. At this point, I would like to go back to Einstein and talk again about these parameters. We talked about these parameters that need to be understood. So Einstein had a dream. And basically he said, if we have the ultimate theory of the universe, one beautiful equation that explains everything, that equation should not have parameters. Because then we'll have the question that we have asked many times during this talk, what determines the parameters? Why do they have these values and not other values? And he phrased it like that. He said there are no arbitrary constants. Nature is so constituted that it is possible logically to lay down such strongly determined laws that within these laws the rationally determined constants occur. Not constants, therefore, whose numerical values could be changed without destroying the theory. In other words, everything should be determined. All the parameters that we know, like the mass of the electron, should have a rational explanation. Everything should be. So this was his vision. And this is a long-term goal, and it might take a long time to achieve it, but we should keep it in mind as something to aspire to. Having said that, I would like to bring a historical cautionary remark. And the cautionary remark is a slide I presented earlier in this talk. So remember that Kepler had this beautiful theory of the size of the orbits of the planets. And this was deep mathematics. And it was supposed to explain why we have 6 planets and not 7 planets. It was also supposed to explain the radii of the orbits of the planets. And it turned out to be completely wrong. Not only is the theory wrong, the question is wrong. It's wrong because these numbers are not that significant. These numbers are peculiarities of our solar system, and there are other solar systems that have other values of these parameters. So this leads to a possible paradigm shift in our understanding of physics. And the paradigm shift is that the universe is a lot larger than we thought. Just as we are one solar system, we're on one planet, in one solar system, in one galaxy out of many, maybe our entire universe is one universe out of many. So there are many universes, and there are different laws of physics in the other universes. The mass of the electron could be different in the other universes. The forces could be different. Maybe they have different elementary particles. We have 3 dimensions, maybe they have 6. So there could be all sorts of other universes, and therefore trying to explain some of these parameters that we still don't understand might be as misguided as Kepler trying to explain the origin of the parameters of the solar system. Now, this idea is rather controversial. Some physicists love it, others hate it, but it's certainly a logical possibility. And I, for one, would like to know whether it's right or wrong. This is a question, it should have an answer, and I hope it will be answered soon. And by the way, the 2013 STAG lecture was given by Lord Martin Rees, and he talked about precisely this topic. So as I said, some of the parameters we might want to explain are not fundamental, and they are specific to our region. So now it's the time to wake up. I'm going to wrap the talk up by summarizing. We've had a long journey. We started with the ancient Babylonians and their quest to understand the stars. And we went all the way through today with lots of historical examples. And I even presented some vision for the future, some futuristic ideas. We have covered huge range of distances. We talked about the shorter distances, it's the Planck scale and the distances of particle physics, and all the way to the universe as a whole, and even further, perhaps there are several different universes, many different universes, with different values. So we have two experimental standard models, two successful standard models, one for particle physics and one for cosmology, describing the whole universe. They work extremely well. This is almost unprecedented success. That's what I said earlier. I made the analogy with Kelvin's talk in 1900, where there was also unprecedented success, and it was wrong to rest on the laurels because huge developments came afterwards, and we can expect that there will be such developments soon. It is clear, I gave enough arguments why it is clear that there must be new physics beyond these standard models, because we have all these little things that do not quite work, like Kelvin's clouds of these models. The biggest challenge is to combine these two standard models to understand quantum gravity. And perhaps easier problem, a simpler one, is to explain some of the observed pattern of these parameters. I say easy problem or simpler problem, they're not simple. And it might take decades to understand them. But fortunately, there's new experimental input soon. And I'm also very encouraged by so many young people in the audience. One of you will jump on these problems, not in the far future, but within a few years. Any one of you can solve any one of these problems, and it will be enormously exciting. So the future is guaranteed to be exciting, so stay tuned. And I very much hope that as many of you as possible will participate in this exciting effort. Thank you.
Thank you very much, Nati, for this very inspiring lecture. I think we'll soon open the floor for questions, but before that, I would like to give you a small gift. As I said in my beginning comments, I think the one thing that most people attribute to you is this idea of dualities. And you did not talk about this in your talk, but we wanted to give a gift which is both personal enough and also try to give the feeling of what dualities is. And here is our gift. And now I want to invite Professor Taylor to give you the gift.
I'm eager to see.
So this is indeed meant to convey the idea of duality. So it's looking at Nati from two different ways, representing the way that Nati has told us to look at physics in two different ways. So this is commissioned from an artist. Hopefully, if you don't like it yourself, we are assured that your family will.
Did you check with? Thank you. Oh, come on. Thank you.
Okay, so now I'd like to open the floor for questions. Yes, we will just wait for the microphone.
Hi, I've read about the possibility that negative mass might be part of the solution for dark matter. What do you think about that?
I'm sorry? I couldn't hear you.
Sorry. I've read about the possibility that negative mass might be part of the solution to dark matter. What do you think about that?
Well, I don't know much about it. Never heard it. The most conservative view about dark matter is that this is another kind of particle that we never heard about, which could be out there, and which you just need to understand what this particle is. There's a even more conservative view These are little stars that are so little that we just don't see them, or maybe they're black holes, and they give us the remaining dark matter. There are all sorts of crazier possibilities, and I think at the moment we should just keep an open mind to various possibilities, and hopefully this is a question that I'm almost sure will be answered in the relatively near future, because I don't think it should be anything crazy. I think it should be something we should just look harder, and there are experiments looking for dark matter particles, there are experiments looking at the sky in more detail, so something is guaranteed to give.
Okay, yes, the one back there.
Is it possible that instead of actually there being just one universe, that there could be two different sort of like parts of our universe, the quantum universe and the macroscopic universe, both having like different laws of nature that are separated by some form of quantum barrier?
Well, that's perfectly possible. And in this picture of the multiverse, that's more or less what we have in mind, that there are many universes and they're separated by some barrier, and we live in one of them. And there are other people giving similar talks in the other universes, and they don't understand why the mass of the electron is what it is, and it's completely different than ours.
Yes, up there.
Is it possible that the electron is not a fundamental particle?
Yes, it's perfectly possible. And what we can know for sure is that if it's not a fundamental particle, it's very, very small. Because we can measure the radius of the electron, and I said that we understand nature to very short distances, and at that scale, the electron looks like an elementary particle. In fact, for the case of the electron, we can push it even a little bit further, and the electron is elementary up to much shorter distances. Now, what happens there is anybody's guess. It's very hard to make models, even theoretical models, that make the electron a composite particle. Definitely not a composite particle like the helium atom is made out of proton and an electron. Or even the proton itself is made out of quarks. So it's very hard to make the electron a composite in this sense. But there might be a more abstract sense in which it is a composite. But we don't know, and once we look with better microscopes, namely better accelerators with higher energy, we might be able to answer your question. Again, there will never be a complete answer until we have a complete theory, because it can always be that the structure is at even shorter distances. But we'll be able to push the envelope further.
There's a question down here.
A century ago, back when you had Einstein and Pierre Marie Curie coming up with their ideas, these theories were developed by individuals, by single people working in concert with small groups. Nowadays, you have massive scientific collaborations, LIGO, etc., that are bringing together an enormous number of people for what seem to be only a similar value of scientific data. Does that mean that because we're putting together larger collaborations for what seem to be diminishing returns, does that mean that the way that we have to do science, the way that we approach answering these problems is going to have to change fundamentally?
Okay, this is a very interesting question. So let me first break it to pieces. These are separate questions for doing experimental work and theoretical work. You brought Einstein as an example. He was a theorist. Theorists today work with 1, 2, 3. There are sometimes papers with 5 authors. It's very rare to find a paper with more authors. So these massive collaborations that you talked about are experimental collaborations. Now, even in theory, but even more so in experiment, things become more and more technical and more difficult. And it's getting harder to find an individual who has all this know-how and all this knowledge in his or her fingertips. For that, you need collaborations with different people bringing in different expertise. So in theory, it could be somebody who gives a good idea and somebody else who knows how to do complicated computer calculations. Now, I wouldn't put the phrase diminishing return, because we don't know what the return is. When you are in a factory, you create something, you put X pounds in, and you got Y pounds out, and you can know what the return is. In science, it's much more complicated. And the return on science over the years has been huge. All the technology around us started its life from fundamental physics. And so some of the fundamental work in early days of quantum mechanics gives the quote-unquote return today in selling electronics. Some of the work of Einstein's theory of gravity, even that works in GPS. So where do you put the return? This is very, very complicated. So I wouldn't use the phrase diminishing return in the context of science. For example, decoding the DNA was a massive project. A lot of people worked on it. Would you use the phrase diminishing return for this effort? We would find cures for diseases, and this is enormous return. So if you use a factor of 2 in the size of the collaboration, or even a factor of 1,000, that's nothing. But what I really find troubling is the phrase of measuring science in this old-fashioned way of and even some universities, they try to have a budget, the money flows in, money flows out. This is good for the business school. This is not good for science. Science should not be run using spreadsheets. And I hope I don't offend the university administration.
Yes.
My question really not follow up to that. My question is very much around if the standard model of cosmology is helping us to understand the universe, is it worth scientists spending time understanding who created the universe?
Okay, again, I'll have to slightly rephrase the question. The question we are trying to understand is not who created the universe, but how the universe was created. I don't have any preconception about whether this is a man or a woman or a god or a Christian god or a Muslim god. This is not science. Now, the way I really understand your question is whether this is an effort worth pursuing. And the answer to that is absolutely yes. First of all, what makes us different than other creatures is that we are curious. Human beings are curious and they want to understand the universe we live in. Second, many scientific results looked totally useless at the time they were achieved. Many scientific questions that were pursued looked totally ridiculous, and they ended up being very important. There's a famous story about Faraday, and I know some people question whether it actually happened, but whether it happened or not, it's a good story. So before he became famous, he was British. So before he became famous, he ran his experiments, and government officials came to visit him, and they looked at the lab, and they were very impressed, and they told him, Mr. Faraday, I don't think he got any knighthood or anything at that point in time. This is all very nice, but what is it good for? And his response was, I don't know what it's good for, but I'm sure that one day you will collect taxes on it. So I think it's really limiting to think of fundamental science as what it is good for. Historically, Maxwell's equations were not good for anything. In fact, it was even questioned at the time whether it will ever be measured. He added one more term to the equations, and it was questioned at the time whether this term will ever be measured. Now, the whole set of equations are central in physics, and they are central in modern technology. So we don't know what the answer is. And the way applications come could be in a very strange way. We'll think about the origin of the universe. This will give us some other idea, and the other idea will have a lot of implications. And the history of science is full of such examples. Finally, the money that is put into fundamental science is completely negligible in the big budget. If you ask what mankind spends on wars, on all sorts of ridiculous things, on even useful things, the budget the universe, the mankind together puts into fundamental science is a tiny, tiny fraction. We put money into art. Is this useful? We put money into all sorts of humanities. Is it useful? No, it's not useful. Should we put money into it? Absolutely yes. Here, the case is even stronger. Not only is it like putting money into music or art or history. Why should we study history? Here, it also has applications. So I think the case is extremely strong for funding science. And you cannot separate between fundamental science and technology. Some people like to say, oh, technology is wonderful, but fundamental science is not useful. You cannot have advances in technology without good basic knowledge and exploration, and you cannot teach, I don't think you can teach engineers without good physics researchers teach them physics, or without good mathematicians teach them mathematics. I think this separation between what's useful and what's not, what will give money in a year and what will give money in a decade and what will give money in a century, this separation is misguided.
Yeah, there's a question there. There's the microphone on that side.
Just want to ask about the idea of the multi-universe. As I understand it, it refers to parallel universes so far away that we can't detect them. It's hard to see how we will ever detect them. I mean, I'd like to know if you think there is some way we will get evidence of them.
Well,
and
yeah.
If not, it raises the question, is it a legitimate concept for physical theory?
Okay, so first of all, even if we cannot detect it directly, there might be indirect consequences that can be detected. So we'll not be able to see the other universes, but there will be other indirect consequences that can be measured. And one thing I've learned in my short life, but even more so by looking at history, don't underestimate the ingenuities of the experimentalists. They will figure out ways to see things that you think are impossible. If I look at experiments that have been done during the last few years, if you asked me 10 years ago, not to mention 50 years ago, I would have said this will never be happening. I thought gravitational waves will never be detected. I thought that the picture of a black hole will never be seen. I was convinced of that. And not just me, people who know better than I said, oh, we shouldn't fund this because this will never work. Now, in hindsight, it's very easy. Of course it works, and of course it's good that they funded it. But beforehand, that wasn't clear. Similarly, for the multiverse. The fact that today we don't see a direct way of testing it does not mean that in the future we will not see a direct way to test it. Now, maybe they will test it and they will say it's there. Maybe we'll test it and say it's definitely not there. I'd like to know the answer.
Yeah, there's one here. Microphone over there.
Do you think we will see a graviton?
Absolutely, there exists a graviton.
Do you think we will see experimental evidence for graviton?
Well, to detect a single graviton, I do not yet see how to do that, but this falls into this category of things that I have no doubt that they exist. Once we have quantum mechanics and once we have gravitational waves, graviton is just a single quantum of gravitational waves. So once we saw gravitational waves, there is no doubt that there is a graviton. Now, there was no doubt that there are gravitational waves even before they were detected. Nobody doubted it. It's not that somebody says, I like Einstein's theory of relativity, but maybe there are no gravitational waves. This was not even a logical possibility. Now, it's very nice that they detected it, and it's a very major advance, and it will have a lot of impact. Nobody was surprised by the fact that gravitational waves exist. That was not a surprise. Now, the next step is having a graviton. I do not know how it will be detected experimentally. I have no doubt that it exists.
Yeah, there's one over there. Here, this row. Yep.
How do we know that there are no more particles? Like if we had this talk a decade ago, we didn't know about the Higgs boson.
How many years?
If we had this talk a decade ago, we wouldn't know about the Higgs boson.
Yes, so a decade ago, people knew that the Higgs boson should be there, and there was even a range of mass that it should be in that range. I don't remember exactly, it was 10 years ago or 8 years ago, or in fact, it was discovered in 2012, so 8 years ago, the range was actually quite small. But if you ask, say, 20 or 30 years ago, even then, there was no doubt that the Higgs boson exists. There were various other possibilities of something even more sophisticated than the Higgs boson. But something had to be there in some range of masses that was more or less understood. Now, you could ask another question: how do we know that there are other particles?
That was my question.
So I assume that that's what. So first, let's get the history straight. We don't know if there are others. And for all we know, there might be nothing up to very, very high energies, or up to very high mass. It would be hard to imagine that today, in 2019, we know all the particles there are, and that's it. From this moment on, there will be nothing new. That's hard for me to imagine.
Is there a possibility that there are an infinite amount of them?
If you could put the microphone.
Is there a possibility that there is an infinite amount of them, or an amount that we cannot count?
Okay, so in the context of string theory, there are indeed many, many particles with increasing mass. Maybe this is right, maybe this is wrong. The heavier ones are very unstable. So they exist tiny fraction, and it's even not clear to what extent we can call them particles. This is getting into an area that we really don't know. I tried to separate in the talk between things that we know for sure and things that are slightly speculative and things that are completely wild. That's getting into the more speculative part. This is worth exploring. In fact, what's worth exploring are precisely those things that we don't understand. We don't explore the things that we do understand, because we already understand them. So for the younger people, I would say the things that one should focus on are precisely the things we do not understand. First, learn the things that we do understand, and then go forward.
There was one here, and then one there, and one there. Yeah.
Hey, I read a little while ago Lee Smolin talking about string theory and possibility that's leading us down routes that aren't going to actually help physics and actually holding us back and possibly stopping us seeing alternative dualities that might link together cosmology and particle physics. Do you think there's a risk that that's the case?
If there are new ideas that string theories are not aware of, the answer is absolutely yes. Whether the ideas that, I'm sure there are more ideas that we don't yet know about. I did not attend this talk that you mentioned, but
It was a book he wrote, but it was back in 2006. So
it's still true that I have not attended that event or have not read the book.
Yes.
But I doubt the ideas that are pushed forward there will play a crucial role.
So you think string theory still deserves a lot of attention and a lot of research investment as well, or do you, because the concern there was that string theory is causing so much focus and actually had so many possible avenues that could be explored.
Okay, so as far as the resources, as I said before, it's tiny. The resources that goes into string theory is really tiny compared with research. We don't need big accelerators, we don't need any labs, we need laptops and maybe an office. This is not a lot of money. Now, how we should direct budget in resources, this is a very interesting question, and I think we should put them where there are results. You don't want to have full results, because otherwise, if you understand everything, there's nothing to explore. But you see, where is the good track record? And the track record in string theory is absolutely spectacular, and I would say that it already has more than paid for the investment. The impact it had on other branches of physics and mathematics, the impact has been enormous. And I don't know how many mathematicians or professional physicists there are here in the audience. It completely revolutionized some ideas in condensed matter physics. It completely revolutionized branches, some problems in mathematics, even in different branches of mathematics, pointing connections, surprising connections between different branches of mathematics. So it has already paid off. So standing here and justifying the research is already paid. That's not the main goal. The main goal is to understand quantum gravity. But along the way, there have been enormous impact on other things. So it already paid for itself. This is to be contrasted with other ideas that are not nearly as good. Now, should the other ideas be explored? Yeah, why not? Maybe something good would come out of it. Whether half of the community should be working on it? Probably not.
In the future, when in the unforeseen future, when science problems become hard to solve, do you think humans would force their own evolutions to be able to solve and adapt to those problems, or do you think they'll become one with the tools that they use?
I wish I knew the answer. I wish I knew. I don't know how humans will interact with robots and AI in the future. I have no idea. And whether this will happen before or after we understand the universe completely, again, I have no idea. Maybe the robots will understand it completely.
There was one in the back, with the black shirt back there.
What would be the most worrying scenario of discovering unified variables and connecting the quantums with the cosmos?
Well, I think that the most promising scenario is based on string theory. And I also would dare to say that this is not going to happen in the very near future. And I really hope I'm wrong about that, in the sense that it will happen in the near future. And this is a very long endeavor. This is not something we should expect to solve very soon, but I'm sure that along the way, there will be a lot of excitement. So for the younger people here, if you think of a science career, this is really, really very exciting, and I'm sure it will be rewarding.
Yes, over there.
Thank you. Quantum physicists have been advised to shut up and calculate. Do you believe that ultimately the universe is actually understandable?
Okay, so the shut up, let me first explain to the people who don't know what it is. Quantum mechanics is not intuitive to us. But we have very clear rules how to compute, and the quantum mechanics gives unambiguous answers. So when people used to ask, oh, we don't really understand that, the response was, shut up and calculate. You don't need to understand it intuitively. We know how to calculate. We calculate whatever we want. We get answers. Now, I am a strong believer in that view. Our intuition was designed on everyday life, was created through evolution, through phenomena in everyday life. And there is no reason our intuition should be capable of, quote unquote, understand things that we are not tuned to understand. But we have math that tells us how to compute things. So in that sense, I don't think we need to worry about intuition. The other aspect of the question is that there are some foundational questions in quantum mechanics that are very confusing, that go beyond our intuition. So there I can no longer hide behind saying, I'm incapable of understanding it, but I really have no problem. I just calculate and find the answer. There it is clear that the answer of shut up and calculate does not apply. Most of this discussion, I think, is somewhat misguided. But there is one place where it might be relevant, and that's when we discuss the universe as a whole. When we discuss the universe as a whole, or the quantum mechanics of the whole universe, there I think we really have a gap in our understanding. And there I think it is something that should be understood better. And there, a comment like shut up and calculate, there I don't think it's valid.
last question, especially if it comes from a yes from a younger person. Yeah, thank you.
If we had a complete understanding of how the universe worked, do you think it would be possible to create a smaller universe inside our universe?
Well, this is not going to happen tomorrow. I don't know. This is a very interesting question. I don't know, but since it will take a long time, people will not remember my answer when it happens. So I will not end up being wrong.
Okay, yes.
Do you not believe that fully understanding the universe? In your previous answer, you said that before humans actually understand everything in the universe. Do you not believe that would actually be bad for us as a whole society and as a human race? In the form that you said that we, as a human race, we have this thing that we're curious, that we want to know more, we want to learn more. If we understand the whole, do we kill off a part of science that is beneficial for us in the long run?
Okay, this is really an excellent question, which fortunately we don't have to address now. But let me say a few words about it anyway. There are two senses in which we can understand everything. One sense, we'll find this ultimate theory that explains quantum mechanics and gravity and the cosmos as a whole. This might take centuries, but imagine somebody brilliant comes along and write the equations tomorrow and we all celebrate. There's a long way to go between that and understanding the universe. So there's another sense in which we would like to understand the universe. And this is, we said before, we understand it in principle. We know the equations, even for the things we do understand, we know the equations, but the equations are too complicated to be solved. So for example, we know the equations in quantum mechanics that describes the motion of electrons. If I take a new material in the lab, I cannot predict what the material would do. After all, it follows from these equations. We understand the equations and we don't think the equations are wrong. What happens is the equations are very complicated. They have many variables and we just don't know how to handle them. Now there are techniques to deal with that, and there's progress in that, and new materials are found and they exhibit new phenomena, and this is a very vibrant field, very exciting, and it even has technological applications, so it's wonderful. And that is something that I think will be even longer to fully understand. To understand the basic laws, I think, might take a century. This sense of understanding will take far longer. So I cannot answer that. And then there's the fact that artificial intelligence can come in and robots, and maybe they will understand it faster. And then we might not even be able to understand it. But this is not something that I think we should worry about in 2019. Maybe in 2020, but not in 2000.
There's one question here.
I should say one more thing about this question and the previous ones. I've given similar talks before, and usually people ask me about the talk, and these questions actually excite me more because you think big, and it's very important to think big. What it will really be in the far future when we understand this or when we understand that. And I think this is the way to make progress. Think big, don't think small. You can think small later, but especially when you're young, think big.
Yes. So, do you think that with our increasing knowledge in science, could we derive from that a sense of moral code? And if we could, would it be an improvement on what we have right now?
I'm sorry, I didn't understand the first half of the question.
Yes. So, with our increasing knowledge in science and objective truth and the things around us, could we derive this to form a moral code? And if so, would this be an improvement to what we have now?
Honestly, I don't know.
Okay, thanks.
Okay.
Sorry.
So, okay, last question with one of the students. And then, so there is a refreshment outside. So after this question, we go outside. We also have a poster session for some of our PhD students, display the research done by the center. So let's hear the last question.
Will Brexit affect our collaboration with other European countries in science?
Sorry, what was the question?
Will Brexit affect our collaboration in science with other European countries?
I certainly hope not, and I'm very concerned that the answer is yes. Now, if you ask me if I have an opinion on Brexit, I have no idea. To be honest, I follow the news and I do not understand. It's really beyond me. Physics is so much easier than the politics of Brexit.
Okay, so let's thank Nati again.